Okay, so just before finishing the session, because one of the doubt one of the candidates asked, I think, uh, I think because I was saying that it was a ratio of two squares, and I was under the impression that the ratios are coming from some parametric setting, but it's actually utilized in order statistics. So, Anshuman, the question that you have asked, the Shapiro will should the parametric non-parametric? It actually should be non-parametric. Okay, so. Uh, Hello, Anshuman. Yeah, I think I'm not sure what was the participant's name, but yes, it utilizes the order statistics, so it should be actually non-parametric test. So I think I have told it is a parametric one.
Yes,
So
yes, sir. Absolutely.
another yeah, because it was a ratio of two squares, but in the ratio there actually it is utilizes the order statistics, so it should be non-parametric. So another part, I think one more thing is that I would suggest you all that you do a simple experiment. The random, now you know how to simulate random multivariate random variables, right? Using R, either by inbuilt option in R, or either by the what is called as a mm, uh, the singular, either using the spectral decomposition or by using the Cholesky decomposition. So three ways you know now. I want you to do a interesting experiment that you simulate a random sample of size 5 and perform a Shapiro test and to check whether it is a multivariate normal or not. The same you do for 5, 10, and say 20, 30, and like this 100. Okay, and you check whether whether the results is giving as an indication it is a whether the underlying distribution data distribution follows normal or not, right? So you test this with varied sample size n. Now next you do for each sample size you replicate this process to identify the count or approximate count that or proportion that it is giving you the correct result. And that would probably give you, and I would like to hear from you all that what is the important indicator, what is the important information about the Shapiro test actually you are getting. So you can later you can drop me an email also, because this is something which is written in many places, but people most of the people don't know actually how to execute that. So we have recently executed that to give some talk to the people who are explaining statistics to non-statistician people. So I think if you just do that part, many interesting properties about the Shapiro test will be clear. Okay, so just as an exercise, I'll formally write also and share it with this with the part of this document. Okay, so then it will be more interesting part of that Shapiro test will also, rather than parametric non-parametric, how it performs, that will also be very clear. So I'll write it and share it with this. Now, what is its connection with the total variance that with this eigen? What is the principal components that we have learned? So the total variance means that the sum of the diagonals of the diagonal entry of the eigen of the variance covariance matrix, which is nothing but the sum of the variance of the original one. And this is nothing but, we know that trace of a matrix is nothing but sum of the eigenvalues. So again, this is sum of this, but variance of y1 is lambda 1, variance of y2 is lambda 2. So variance of sum of this is also again turns out to be the sum of the variance of the principal components. So that means the total variation within your original predictors and total variation within your linear combination of the predictors, which is the principal components, they remain same. But interestingly, it is we give from this gives us a very wonderful result is that the how much proportion of the variation is being explained by the first principal component. So total variation is sum of the eigenvalues which is in the below, and proportion explained by x1 is lambda 1 divided by this. So one may interested to look at that the total proportion of variation explained by the first k principal component is equal to, so if add up the first k many eigenvectors or eigenvalues and divided by with the corresponding the sum of all the eigenvalues, right, which is nothing but the trace of the matrix. So here I wrote little bit of description that why these are the things very important. So what are the most common use of them? That there are too many explanatory variables related to the number of observations, and there is a presence of multicollinearity also. And we may observe that only some of the eigenvectors are actually enough. Only some of the principal components, first few principal components, are enough to declare that what is going to be the, like, how much proportional deviation we explain. So, for example, if your data has 1,000 many columns, and it has a certain total variation which you can get by adding the sum of the diagonal entries. Now suppose that first principal component and second and third principal component itself explain 90% of the variation in the data. So that means instead of going to the further analysis with the all 100 or 1000 variables, you just take three columns which are nothing but the principal components of the original vectors, which is y1, y2 and y3. That should be more than like that contains, that captures almost the whole variation in the data. So this is something. Let us go back to R. I think this may, you can, if you want, you can write this down also. So I think this is a data which is very commonly you'll be finding. So you can have a view of this data. Sorry. You can have a view of this data. This is US deaths, accidental death, not this one. View US arrests, right? So this is a view of the data. You can see that these are different regions, that what are the crime things are happening, and these are different types of crime, and right, this is the view of the data, and this is the function. Now actually you all know how to do it, even if the function is not given. At least we prefer to do it. So then you get a this PRINC comp. This basically performs the principal component, and if you print this PC, you see that a lot of things, some output you have got, right? So component 1, this one, component 2, this, and component 3, this one, and component 4 is this one. So these are the standard deviations of the component. As you observe that first component has already, it's a very large values, right, as compared to others. So that means first one component itself explain the lot of variations, right? So let me just get into this setting. So there is something called as a PCA biplot, right? So this is actually the principal component 1 is the along x-axis. So let me zoom it. Right? If you observe the principal component 1 and principal component 2. So this is the axis for y1, the axis for y2. Now as you observe that this vector assault, so this variable assault, this principal component 1 is almost parallel, right? So that means the maximum deviation, right, is almost explained along the direction of assault only. So principal component, in constructing the principal component, this direction is very important. Please understand. This direction along horizontal means, because that is with the for applied scientists, this is the justification you have to write in our research articles. So it is along this direction means along the principal component 1, the assault has a maximum variation over there, or the maximum contribution there. So if we write down the component 1, principal component 1, as a linear combination of these 4 predictors or 4 variables, then assault is its coefficient is going to be the very high, whereas these are the murder, rape and other, these variables will have a very small values. And this r1 pop, this is also going to have a very small value. Whereas if we come to the component 2, and this right side direction means it is actually positive, the coefficient will be positive. Whereas in principal component 2, its construction, assault has no contribution over there. It's basically, it's just as a vertical to it, right? It's a vertical line as compared to 2. Whereas R1 pop has slightly, is all the contribution to principal component 2 are made by actually R1 pop, and it is a negative contribution, because if the arrow would have been in the top side, it would be a positive contribution of the R1 pop to the principal component 2. Below side means it is a negative contribution of the component 2. Is the graph clear? Is the description got clear? Yes, because this is very important, that which are the predictors, and this inside this 2, which is a very small value, they are not contributing significantly, neither of this component 1 or neither of this component 2, right? So this is a very important plot, which is called as a PCA biplot. In, if you are analyzing some real data in general, this is always this to be reported in research article also. Now let us try to some of the data set which I have already shared with you. Let us try to have a look at this. So what is the data? Let me just show you the data first. So you will not be having these row names in the original data. It's an Excel file, it's a text file which has been sent to you. That the data I'm reading over here, read.table comment, using that you can read it. And if you can try it actually, if you're in your own PC, any trouble comes, you can ask me. So this is the data I have read, right? Then if you read this, if you just see this head of invest, so you get only this one. So these variable names are not clear, and also for each column is basically managed by, is representing one company. So that company name is also not there. So this is the complete raw data has been given to you. So here in the original code, I have put it over here. So these are the row names. I can take actually row names over here. And now you print the some values from there. So you see that the first row corresponding to this company. Third row corresponds to Bank of America. And similarly, you can also set column names. Right? Now you print some of your. So now you see that you get, this is the view you have got. So first row or third row corresponds to Bank of America. First entry corresponds to US stocks. Then the second entry is the non-US stocks, right? Then third one is the some other variable. Then again certain things in bonds, when US bonds and non-US bonds, right? This is what it is. I think this one will be bonds non-US. Let me just correct it. Okay, so now if you view your data, if you view this data, invest, this is actually the data set looks like, right? So this is the data which has been shared with you, and after you run this code, you will also get to learn that what is the actual row names and row columns, right? So let us try to understand this a perform a principal component analysis. So this, okay. So you get a summary of the this principal component. As you see that this talks about the this importance of this. What are the like these are component one. There will be 8 component, right? And what is the dimension of the data? Dimension of invest 8. So there are 8 variables. It has given you 8 many components. But how many components are actually enough? Say for example, if you read this proportion of variance explained. So the first component explained approximately 64%. Second component approximately 16%. The third component approximately 11%. Rest of them are only 3%, right? Then 2%. So as you see that first of this, right? If we just add them up, 92, right? So approximately 92% of the variation in the data is actually explained by the first 3 principal component itself, right? So you can, then we can have the, there is one called as a loadings of the principal component, that I'll talk to you when we talk about factor. Then you can also have a look at the variation associated, standard deviation associated with each of the principal components. Okay, now this is a small exercise for you. That can you connect, anybody can tell that, can you connect the standard deviation with the variance covariance matrix? Anybody? Play with the way. Yes, please. Covariance matrix of the data.
These are eigenvalues of various covariance matrix.
Are you sure eigenvalues or something? Some only
Oh,
eigenvalues?
sorry. Square. I think.
Very
Square.
good, excellent. Very good. These are nothing but the square root of the eigenvalues, right? So play with the covariance matrix of the data and the PC output, and try to generate the results using just without using any packages. Also report whether any discrepancies you are getting or not. Okay. Okay. This part is done. So this is what we have. Right? So from the output, we see that the first 2 principal components actually explain approximately 80% of the variation in the data, right? So can we just have a look at this summary once again? Let us look at the summary once again. If you see the third row actually talks about cumulative proportion. So first component 64%, first component, second component together, right, is 80%, right? First three together is a cumulative 92%. First 4 95%, right? So there is something called as a scree plot, which actually plots this directly for you. So this is called as a scree plot, right? Yes. So these are talks about the component wise the variances, how these guys are like dropping, right? And you can get these values also, and you can create a values also with the proportions. So you can get one such plot also with the proportion, right? So this part also I request you to do this, because that is also a very commonly used picture. So this just nothing, they just plot this cumulative proportion in the same plot. So you get one plot like this which goes to 1. That's it. Nothing else. Okay. So as you observe that after component 3 or after component 4, there is almost no changes is being observed. This is also another very important plot which is usually reported in the research articles, particularly for application oriented research articles. So when you are analyzing some ecological data or some environmental biological data, and this is a biplot for this. So as you see that a lot of pictures are there. I can make this picture little bit readable more if I make it 0.60 and this may be 1.1. So yes. So as you observe that first principal component, most contribution are coming from the US stocks, right? And it is a positive contribution. Whereas the alternative investment strategies, it is having a negative, significant contribution, but it is negative. Whereas this bonds, US and others does not have significant contribution along the first principal component. Whereas the second principal component, you have the most contribution of the bond US, but the contribution is negative. Whereas other predictors does not have that much significant contribution. This is, if anybody is from psychology or psychometry in this domain, this is one of the most important plot, and you must represent it, because there we try to align depending on the loadings of that we'll talk about it. Even the loadings, we try to assign that whether some of the particular variables can be labeled as a single factor or not. So that solely depends on the how much loadings it is getting. So in the first principal component, the loadings for stock, US and alternative, they are very high, whereas these are very small. And US stock loadings is positive, and alternative investment strategies loading is negative, but it is significant. Okay, I think I could make sense out of it. So this is, now let us just as a from principal component, automatically the next things that comes up as actually the what is called as a factor analysis. I'll show you after telling it. I'll show you some of the case studies also that what we have done. And definitely we are very open to share the codes, so no issue at all. Everything will be in your hand. So this one is that I put it over here so that later you can read it also. So these codes are over here. This is the actual data. This is the deviations. That is the picture what I was explaining. That stock in the component 1, stock US has a very high positive contribution. A right picture that you have observed. This one, right? Whereas others have very small contribution. Then again, alternative investment strategy has a very significant one, very high loading, but negative. So its direction is negative. So why actually spend it so much of time? Because at least 2, 3, 4 workshops we have taken, and one of them I definitely in the School of Social Sciences in Assam Agricultural University, we had one workshop, and we understood that all the analysis with the psychometry analysis with students and the understanding different level of over there. So this is the analysis which is most important for them, and we have actually taken a thorough full day session on that for the practitioners there. So this is what it is. This is the script plot, factor analysis. So factor, let us just try to understand little bit of historical idea from it. So most of the statistics students, they definitely know about this Johnson and Wichan book for applied multivariate analysis. So I'm not sure, because every time when we read a book, we go into the problem and analyze the data and we finish it there. The introduction part of this factor analysis chapter is very important. It says that factor analysis has provoked rather turbulent controversy throughout the history. Why is it controversy? Because when you deal with financial data, only environmental data, everything is fine. But when actually deal with the cytometry data, you are trying to define what is intelligence. You are trying to define what is the measure of emotional intelligence. So different type of intelligence you are trying to define, and you are doing a lot of different experiments on human beings, and you are trying to come up with some kind of measure that what is IQ, what is this emotional intelligence, what is this measure, that measure. Those definitely leads to a controversy. So when they have actually started working on it, like Carl Pearson, the Spearman, these are the big names, you know that it initial time it had been a lot of controversy over there because they are trying to define that measure of intelligence. So in modern beginnings lies in the 20th century attempts of Carl Pearson, Spearman, and others define the measure of intelligence. Because of this early association with constructs such as intelligence, vector analysis was nurtured and developed primarily by scientists interested in psychometrics. So main contribution comes into the psychometric. It also says that arguments over the psychological interpretations of several early studies and the lack of powerful computing facilities impeded its initial in development as a statistical method. So initially it has a very tough time to be considered as a valid statistical method. However, with the advent of high-speed computing machines like and a lot of computing facilities gone, there has been a lot of theoretical and computational aspect of vector analysis being explored. So now it is, I think, practical in ecology, environmental, and other analysis. This is one of the most used thing. Most of the original techniques that has been abandoned in early controversies, these are resolved now, and now it is a valid method. But it is still true, however, that each application of the technique must be examined in its own merits to determine its success. As you observe that the domain you are dealing with over here, you cannot just say anything. We should not always consider that what our algorithm is giving, because the domain in statistics is very important that the domain we are dealing with, it must go with the same logic as the domain goes. So that's why the domain knowledge is very important. So what basically factor analysis does, the factor analysis deals with a structured of the covariance matrix, and it tries to understand whether the data are consistent with a prescribed structure or not. So basically, covariance matrix has some structure and it tries to understand what is the structure of this covariance matrix and try to extract some information from there. So in general, so this is only for the statistician people, and if we have this is the my vector and mu is its corresponding mean vector, we try to write it down is as is one matrix L, which is P by M, and F is called as a factor, which is an M by 1, and this is the what is called as a specific factors epsilon I, right? So mu I is the mean of the variable I, and epsilon I is called as a specific vector, specific factor, and Fj is the jth common factor, and Lij is called the loading of the ith variable on the jth factor. These loadings are going to play very important role. And as we understand that if are definitely these are unobservable quantities, so these are not going to be observed. So whereas we'll try to align some of the predictors or some of the variables with certain factors, right? So the unobservable random vectors are f and epsilon, and which satisfy certain relationship. Okay. Let us talk with an example. So I think this data also I have shared with you all. That I'll talk about actually two examples. So hemangioma, this is one of the data that hemangioma actually is a most common childhood cancer diagnosis. Okay, so it appears as a lump of blood vessels on the skin, right? If left untreated, it usually resolves within a few years. Some parents opt for a surgical removal also, right? So we have got a registry for the surgical one. So that the what is that the data set says that the age measured in days in the infant's age at the time of surgery, and the age then represent how long the infant was exposed to the tumor. It was hypothesized that the exposure to the tumor might influence the magnitude of the expression of some of these genes over time. So we are going to have some genetic expression data also over here. So how much expressed they are. So you're encouraged to investigate data. So this is very important. This is for what for you, because by now you all have learnt many technical parts, or the experts, different experts, they have given their expert talks on this. But there are certain things which, when you're talking about data analysis, unless we get our hand dirty, it is impossible. So, however, lecture is gone, it is not going to help us. So, you are encouraged actually, the data is provided to you, that investigate the data for possible outliers. Now, you all know what are actually outliers, and perform some exploratory data analysis, and which we have already learned in the workshop. This is an important connection. What result you will be getting now, whether after removing the outliers or other things, whether you will be getting the same thing or not, that you need to check. Had this been offline, then I could actually go to the computers and different computers and check out the things. But unfortunately, here it is not possible. But if anybody is reading that file, so you can let me know if there are any problem or not. Just hold for a second. I think there is some kind of noise is happening. Yes, sorry for the interruption. Yes. So let us first read the data. So if anybody is being hands-on, so let us read this data first. So I think you can read this data, because if you read this, it has names and everything is there already. So if anybody is reading, if you are finding difficulty to read, but one thing is there, this option probably you are already aware of, that you need to give header is equal to true. If you open up this text file, then you see that in the top you have the variable names, right? And whereas when you give it over here, because when you write down, say for example, if you write down help read dot table, you see that default option is header equal to false. So if your data contains already headers, then you have to give it header equal to true. So I deliberately put two examples where header is not there. The first one, where you had to write down the variable names, and by using the option called call names, you can put the name of the variables. Okay. So let us try to do something factor analysis. Okay, on this data. So we got a print of this data, view of this data. This is the function that is called as a factorial. This is the function which is used to perform factor analysis. There are definitely other options. I'll give those references. Right? This is says that, so these are the loadings. This part is very important. That what are the predictors, or what are the variables are associated with the factor 1. So as we observe that this gene, the expression of this gene and this one and this one, they seems to have a very high contribution to factor 1. Whereas in factor 2, this one, the P16 and DLK seems to be very high contribution on this. And whereas for factor 3, only this RB, this one seems to be very high contribution on RB. So that means, and rest other predictors does not seem to, like age and like for example this NaNOG, comparatively small as compared to others, they does not seem to have any significant like contribution in building these factors, right? So what we basically get from here, from this, we examine three factor loading over here. So there, this how many factors to be given, that will be in your hand, right? So three factor loadings, whether consideration of three factors is sufficient or not, that can also be checked. So you examine whether three factor loadings, see that these three, as I explained over there, these three appear to work together with the first factor. Then DLK marker is the for the second factor, and RB marker is for the third factor. So those loadings that we have observed, age plays almost no part, contrary to our original hypothesis that length of time the tumor burden is carried by the patient. Right? That was an important statement that we have made over here. Is that age is what? It was hypothesized that exposure to the tumor might influence the magnitude of the expression of genes of these genes over time. But it seems that this age does not have any significant dependent or cannot be associated with any of this factor 3, right? This outcome is important. So what is this outcome? Let me go back over here. If you see the outcome, the last line, the test of the hypothesis that three factors are sufficient. So that means your null hypothesis is three factors is enough. The chi-square statistic is 8.03 with 7 degrees of freedom. The p-value is 0.33. What to do? Should we reject the null hypothesis or accept the null hypothesis? So we are not able to reject the null hypothesis because p-value is very large, right? So that means it says that the large p-value indicates that three factors are adequate to explain this data. So when we actually jointly write research articles, like because with Assam University we have written articles on understanding the emotional intelligence of this, so that when writing that, it is very important that every output, whatever the analysis has been given, they are appropriately supported with the corresponding statistical outcome. So that must be appropriately reported. So what next actually? A natural question arises that how robust is the factor analysis procedure against outliers in the data. So the question what I have given it to you. So what you are supposed to do over here, what you will do it, that examine the marginal distributions of genetic markers in the hemangioma data. So first thing, automatically you can actually do that. I think this you have already done it. That pairs. These are very important, interesting plot. You all know. If I just put some call is equal to red, let us zoom. This plot you already know, most of you, right? That it gives a pairwise plot for all the variables. So for example, this says that along x-axis I have DLK marker and y-axis I have P16 marker, right? So this part you can see that, right? As this data itself, you get a feeling that probably there seems to be a lot of points which are staying much away from the what is called as the main center of the data, right? So you can also visualize actually that if you write down that the histogram, you can also write down the sum of this. You can plot some of these histograms also, and you try to see that. So this seems to be a kind of a bimodal kind of thing. You can consider some other predictors also, say CMYC. There seems to be something over here, right? So how do you perform a box plot over here? Right? We can easily understand there seems to be an outlier over here, right? This is a complete experiment that I would suggest you to do it. The question is also put there. And after possible that whatever the EDA techniques you have learned till now in this workshop, that by that you identify that what are the possible outliers and remove those outliers, right? And then whatever the remaining data you are going to have, with that you again perform this factor analysis and try to see that which are the factors are have got the most like whether the output that is being presented over here, is there any changes is happening or not. Okay, these parts are very important. Why I just want to spend 2 minutes over here. So what is happening nowadays that when we are uh, because nowadays ready-made codes are everywhere available, and with the data science and ML, what we tell with that we find that lot of Kaggle data and their codes are also available. So people have got a tendency that we take that ready-made codes and run it, and in our output, whatever we have get, that we accept as a final truth. But when started in job, say for example, 15 years back, then with every data, first thing it has to be looking into that cleaning of the data, understanding individual marginal distributions, understanding every bits and pieces of the data. Then actually we go for the modeling. But now since a lot of codes and other things are made available, so immediately people start that four pieces of lines of R code or Python code and try to get the whatever output they get, they try to represent it. But this is not a good idea actually. So this is one of the example I deliberately put that, so that you get your hand dirty also with the problem. So repeat the factor analysis for the process data after you do this cleaning and cleansing part you do. And are your conclusions the same, or how do this differ? And which conclusions you are going to prefer? That is the question that you are having. So similarly, another exercises that we have put, that this is one of the data set library. So you know that I think you are already been exposed to it, that help data sets. Data set is actually package which by default it maintains a whole lot of data sets are actually there in the data set package. If you write a double colon, then you see that all the data sets which are available here, you can actually see it like this. So what is the name of that? US judge ratings. So if you write a double colon, so write US judge ratings. This is the data you have got. So this is the data, right? So if you just get a view of this data, US judge ratings. Okay, so let me just visual. Okay, so what is this data? Let us view it first. Sorry, I did not view it. The cluster over there. So this is the data actually what we are having. Right? I think in the x-axis, in the column row names, basically there are names of the judges, and 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 what are the other information? So if you just write down help US judge ratings, this will take you over there. Lawyers ratings of state judges in the US Superior Court. So description, lawyers ratings of state judges. Format of the data, there are 43 observations on 12 numeric variables. So these are the data description. So what is we call it as a data definition, right? Definition of the variables. So INTG means judicial integrity. DMNR means what is the demeanor, and familiarity with law, and oral sound, oral rulings. So these are different ratings of different judges. So this is also given. So see that pairs function is very common over here. The first thing with any exploratory thing, to start with the pairs, right? The other pairs plot you have seen, the other one for the hemangioma data, here it is much different, right? Can anybody tell me what is the main difference over here in these two?
In all the observation, the trend seems to be the same, no?
Yeah, there is a lot of multicollinearity, right?
Hmm.
So there is a lot of correlated predictors are there, right? These are the very high correlation amongst them, right? So if I think there is some, I'm not sure if you just go into this help pairs, there are different options actually. I think you can put there. There are various options. Let me just check out one or two options. Okay, so this is one of the example. For example, you can take some of the examples from existing one. So I think panel dot keys that I need to define. So they defined a so you can define a function actually, and then you can pass that function in the what kind of function you want in the diagonal panels. So this was the basic pair plot. This was the basic pair plot, right? So here the plot is, if we just plot only the first five one, so pairs, the first five one, so call is equal to red. Okay, this is the plot. This diagonals, and you can make a lot of customization over here. So if we go to this help file, and if you observe that this diag.panel, and what are the things we want in the diagonal, those things you can change it. So we have here they have written a separate function that what we written in the diagonal. So they want it to be a histogram. So then once they plot this over there, they get a histogram over here, right? So this is a very wonderful plot, and this plot is very useful in writing for when you're representing your data description in the journal articles or preparing making in the report. This is a very effective way of communicating. Okay, this is only for the first five variables. Okay, so do the same exercise. So here, what is the exercise over there? So examine the pairwise scatter plot for this data. We can use the pairs comment, and to reveal that some variables that are highly correlated, right? That is what we observed over there. And perform a principal component analysis for this data. So what the PCO we have learned, that will be revised for you. And the first two components actually explain 94% of the variability. That you verify, do it on your own. And the second component is almost entirely the number of contacts, and the first component is essentially all the variables, all given having the same word. And you interpret the result, what it is coming. So if this is taken from a book, but when actually we analyze the data for the Assam Agricultural University, they are trying to understand the emotional, the quotient of various different intelligence for the school children. Uh, the problem is like this only. So if you are dealing with some psychometry data, it turns out to be something like this anytime. So you have to look at this data for very first before getting into any kind of confirmatory analysis. It must be required that you get a complete visualization of the data. So I think is this function being covered over here, that uh, I think core plot, some function called as a core plot. what is called as a correlation plot. So with this double comment also, double colon mark, you can get into actually. So there is another correlation plot, if you can see that. So PSYCH, right? This is one of the very interesting package actually. So if you write down that library PSYCH, and it does provide a lot of multivariate, wonderful multivariate thing, multi-analysis options. Okay. So if you write down that now help for now the core plot you have got over here. So earlier it was not available. When you load the library, automatically the functions within that library will be available to you. There is other way also you can see it, PSYCH double colon. Now see that automatically what are the things are coming up. Okay, what are the functions are there, it is coming up. If you write down core, then you are getting a core plot, right? What is there? US judge. If I just judge ratings, and see that an yellow button, yellow comment, we have got different things, right? Yes, and you put numbers is equal to true, there is an option. Just like try to see what is the basic plot is coming. This is, see that this is the basic plot is coming, and you see that there are a whole lot of uh, like there is a multi correlation is 0.96, right? Some points are very small, some are very big. That means what? This will be more clear to you. Say for example, I am taking only the first 5. So when correlation is small, it is value is the size of the number also small. When the correlation is high, the size of the number is also very high. Is it clear? This is a very wonderful wonderful visual exploration actually for before going into any kind of multivariate data analysis. This is a very common practice that we will do. All kind of information about the data we try to get first, then we go for the next step. Okay, and there are definitely you can now play with this health core plot. If you write down, then you'll be getting a lot of things, and you can play with various different option over here. So whole lot of internal comments it take, and you can play with them and get different informations. So in that actually in this plot in the diagonal you can, there are color code also you can change, you can reverse the things. So many things actually you can play with it. Okay, so now this is, let me, I think now we have talked about already what is called as a multivariate normal distribution. We have learned that how to check whether certain data is multivariate normally distributed or not. We have also learned how we can simulate observations, simulate random variables following some multivariate normal distribution. From my point of view, that the geometrical understanding that we have about the probability density function and how the density function one side is getting stretched, one is getting lower, that is the most important part in my viewpoint that we have understood, because almost all the book will contain that heavy sided matrix algebra and programming, but very less number of books who comes with good visual inspection of the mathematical ideas. So this is also very important for the who are from non-statistics background, that understanding that variability in the data, that is very important, because there is no mathematics here. We just have to understand the codes that we are utilizing, that you play with the variance covariance matrix of the data and try to see different types of plots, pairs plot, correlation plots and everything. Check out distribution of individual variables, and then try to compute the principal components and try to associate the standard deviation associated with the principal components and draw a scree plot, and also interpret that biplot. That is very important for interpretation in practical applications. When writing research articles, if you have collected the data for 2 or 3 years of time, you have given for collecting interesting data, and now because of this Euro database, we now know, because statistician many often say that they don't have that data, we don't have that data. If this data is available, so now how data collection is important and how difficult it is, we have realized while creating this national repository for invasive species. So that is also, that's why when you get the data, give everything, every understanding on the behavior of that data. Okay. So with that we understood factorial, we understood factor analysis also. I think this is some pairs plot we have given. This is one of the problem that we have dealt with. Some time back we have worked jointly with Assam Agricultural University. We have arranged a couple of days program, and then we get access to this data. I think it recently appeared one of the publication published by one of the conference proceedings in IIT Guwahati. So ASB, they have taken the measurement that spatial visual intelligence, then linguistic intelligence, then logico-mathematical intelligence, then musical intelligence, then BK stands for bodily kinesthetic intelligence, then interpersonal intelligence, intrapersonal intelligence, and variable description is very important. What is that? That when they have given us this are only put this much. But we need to find out that what are the description of individual predictors. That's why if you seek help from some statistics people about this, so the major information, the domain information, it is your responsibility to provide it to them. Right? So the PCA that we have done now, today we have only used this. Right? We did not use other options. So there are whole sorts of options that are available in R. Okay, but we have taken the most basic one. Why is that? Because it ensures that our understanding is clear about the topic. Then when it comes to the sophisticated applications, then we try to get more and more complicated packages, because many packages come up with very specialized graphics as well. Right? So this is the data which we have already here I have done it using PRComp. This is another one. So this is the PCA biplot that what we have got over here. As you observe that first principal component, these three fellows, they seems to be significantly related, and little bit concentration from here also. So interpersonal intelligence, they are not contributing to the first principal component, right? And whereas PC2, they are interpersonal and intrapersonal, they are going to have a more contribution. So that means if you try to understand them, so this seems to be kind of a three-factor possibly. That one factor which is mainly associated with LM, SV, and these things, like to be together as a single factor, whereas others, this inter-P or BK may be considered as one single factor that is be subject to variation with validation with the corresponding domain expert, and this intra-P seems to have a completely different one. So this is that's why this PCA blind plot must be reported, because the interpretation comes from here. So of course these are the codes over here is given to you. So this is one of the example which I have just explained to you, that scree plot. So this is, you can have both type of plot, that proportion of variation explained. So first principal component 40%, then right. So these are the variance associated with the principal component. Now this is the, and the y-axis is 100%, means all variation explained. So as you observe that this is the cumulative variation being explained, which is being considered. So depending on the system that you are investigating, that the domain experts may tell you that whether to consider 3 or whether to consider 4. So this we need to keep this in mind, that statistically we'll give some test and something we'll get. But it is also very important that which are the variables which are already known to be very significant in that domain, we should not discard that. Just we recently we had a we are analyzing that KM Hospital Mumbai. We are analyzing their uh, we are trying to analyze whether patient respond or not respond, and they end up with a high dimensional situation. High dimensional situation means number of row is small, whereas number of column is very high. And with that to particular treatment, and they have lot of measurements they are having. So what are the measurements or what are the variables particularly turns out to be important? They we are now like kind of analyzing that, and most of you know probably features in feature selection, lasso, reach, and other elastic net. These methods or random forest. We are with that we come up with a set of predictors, set of variables, or set of markers or indicators. But when we had a discussion with them, they said, no, how this can be cancelled? Because almost all are true. What from medical point of view they thought, but one is not there. Then again, then say that no, this must be there because this is connected with that. So then again, we had to reanalyze the whole thing and actually have to come up with it, to identify where this problem has gone. We had to find up with it. So this is a very important that those particularly those who are non-statistician, if you seek for help from a statistician, you have to be very confident and you have to provide that complete information. So PSYCH library, this also does provide this very important library for doing PCA and factor analysis, everything. So here also this provides a lot of rotation option also it comes up with, where the best rotation it can give you. So this is also a biplot from where you can get this type of picture. And these are some of the interesting plots also you can get actually. So right. So these are subject interpretation, and there are other this database when you perform a factor analysis. So there are different possibilities: the factor 1, factor 2, factor 3, and you know that factor analysis is also going to give you whether factor 1 is sufficient, factor 2 is sufficient, or factor 3 is sufficient, right? So this is the output for factor is equal to 2, right? So if you see the output over here, so it is saying the test of hypothesis 2 factors are sufficient. The chi-square says is 10.34 at 8 degrees of freedom, and the p-value is 0.242. So that means your null hypothesis is whether you should go for a 2 factor or not. Answer is 2 factor is sufficient in this case. Okay. Now these guys are being associated with it. So it is very important that you can actually correlation. You can investigate the correlation. You can investigate the correlation matrix by various different options. So some of the options over. Say for example, if I just so this is one library called core plot. Okay, I think I do not have that library. If it is not there, what to do? You have to go to the package, install. What is that? Core plot is there. So install. Right. So library core plot is now there, right? So what can be the plot options? That core plot, you can find out the correlation matrix of the data. So you can find out that if you can find out the how do you find the correlation matrix? Say US judges ratings, I can take only 1:5, So this will give you the corresponding correlation matrix, right? So let me call it M. And if you write down core plot M, then you have a whole sorts of option is there. So method is equal to, say I'm writing shade. Okay, and you can also give type, different types also you can give. Type is equal to, say, upper only. So this is a correlation plot which you are getting. So as you see that there is various different options over here. So I think uh, method has some ellipse option or something are there. Ellipse is there, yes. So this is going to give you that which are the predictors are these are highly correlated, whereas CONT and INTG, they are not highly correlated. And you see that there is a color bar also. Highly negative means it will be -1, this red one, and the blue one means it is the color. These plots are very important. In particularly for a statistics person when you are communicating with the interdisciplinary researcher from other domain. So as we very closely work with multiple researchers from other domains, so that's why we have to be very careful with it. So as you see that the shading of the colors of the also you can check. Here all the same size, all the correlation values, but shading varies accordingly. So more shade means it is a more correlation. So actually this also provides the correlation based clusters. So since clustering is a part of it, so this function itself they provides a correlation based cluster they provide. So this is actually the function that H class that I'll discuss now is the main function for performing clustering analysis in R. So I think I'll just talk about this. Once we are so I think is there any query related to factor analysis and PCA? Is it fine? Okay. So maybe it is okay. So okay. Then we are talking about the clustering. So what is basically clustering does? Let us try to understand it first. So these are a couple of pictures we just put just to show you that how the clusters may look like. So these are some clusters as you observe that. So these are various different types of view of the clusters may appear. Right? So let me explain it to you from a what is basically. So I'll share the slides also with you. Yes. So what is basically that clustering says? It says that we seek a partition in the feature space into distinct groups so that the observation within each group are quite similar to each other, while observations in different groups are quite different from each other. Right? So if we just look at this pictorially, so one of the picture if you observe, so here two group of, I can see that here two group of data is there because the color is provided to you, right? So we should be able to identify this to be part of one cluster. We should be able to identify this to be a part of another cluster. Should identify that this should put into a single cluster, right? This is what we are going to do, right? So similarity or different. Now how similar they are or how different they are, this is very much domain specific consideration. Right? This is very much because it measures the distance between points. So that means it is going to consider the distance between within the cluster and distance between the cluster between two clusters also. So how to define that distance, that is important. So typically for many applications Euclidean distance is being considered, but there are whole sorts of distances there, Manhattan distance and many other things. So for instance, suppose that we have a set of n observations and we have p features. So the n observations could be corresponding to some tissue samples of patients with breast cancer. And the p features could corresponding to measurements collected for each tissue sample. So this could be clinical measurements such as tumor stage or grade, or they could be a gene expression measurements also. So this is the kind of data that we can have. So what is the PCA? We have just learned in a greater detail. What is the clustering? It does that both clustering PCA seek to simplify the data via a small number of summaries, right? There also we have seen that many of the variables are being clubbed into a single principal component. So lot of like columns all over the space we can save for it. Whereas in clustering also there are a lot of data, but we combine them into certain groups so that groups represents. So once you can identify that groups, our so basically is a kind of a if we know information about that group, that means enough. So distribution of that group is done for us. So clustering looks to find homogeneous subgroups among the observations. And whereas PCA looks to find a low dimensional representation of the observation that explain a good fraction of the variance. One of the common examples in the clustering is basically comes in a market research. So people know it actually. Suppose that we have a large number of measurements, say median household income, occupation, distance from nearest urban area, and so forth. And for a large number of people, this information we are having. Now, our goal is to perform a market segmentation that by identifying the different subgroups of people who might be more receptive to a particular form of advertising, right? So if I create say 10 boxes of 10, if we can identify 10 different regions, so in one region a particular form of advertising will be more useful, in other regions some other particular form of advertising will be more useful, right? So what kind of advertising should I do so that the likelihood of purchasing of some particular product will increase in that particular region? So, for example, in your region there is no television and you are advertising on television, so that region is not going to get anything. So that region will come into a one basket. Whereas in other region where more television users are there, there will be another basket. So the task of performing this market segmentation amounts to clustering the people in the data set. That's it. So there are a couple of mainly two ways people do in a clustering. The k-means clustering. One is the hierarchical clustering. What is actually the k-means clustering? The idea behind k-means clustering is that boost clustering is for which within cluster variation is as small as possible. So if you decide to make 3 k-many clusters and WCK is the variation within the clusters, and you take the sum of these variations and minimize this with respect to C1, C2, Ck. So this is what is the main idea of clustering. You want to minimize the within class variation, right? So for example, this is where I have a 2 clusters, right? K is equal to 2. That here we have 3 clusters, actually 3 different sets. Here we have 4 clusters, right? And what is this one? That this difference, the WCK is nothing. It is the Euclidean distance between the data, right? And where this I and I belongs to the same cluster. So it talks about within cluster variation. That I and I, they both come into the same class. So it is the distance within the same class, and by divided by this symbol means the number of elements in that, or number of data points in that cluster. So it's an average. So then you minimize this quantity, this if you write the complete thing. So here this represents a Euclidean distance, right? But you may have several other possible distance measure also you can have. So we have to form it in such a way that this quantity is minimized. So you randomly assign a number from 1 to k to each of the observations, and this serves as an initial cluster for assignment of the observations. You will start from anywhere, so it really does not matter. And iterate until the cluster assignments stop changing. That you keep on iterating in such a way that there is no changing in the assignments, that putting one variable, one data point into other cluster, that change is not happening till that you run that algorithm. So for each of the k clusters, compute the cluster centroid. The kth cluster centroid is the vector of the p feature means, and the observation the place cluster, right? And then you assign each of the observation in that cluster whose centroid is the closest. So you get a centroid, and nearby points you assign them with the centroid. So this is kind of this. So this is the data you have. This is your step 1. This is your second step. So you, for the full data, you have the all the clusters are actually here. Then your algorithm is running. They are getting separated. That eventually the iteration happened and you got separated. And in this phase, at this phase, you get stabilized. That here no further changing is actually happening. Right? That's how the iteration works. Right? So understand? So when we do that, actually, that as we said that there are several possibilities of distances. So here the distance between clusters can be like this. So this is one distance which is called as a, the A1 is called a single linkage. Second one is the called as a, right, complete linkage. So as you see that this one is the maximum distance these guys are maintaining. And third one is the average linkage. So this is that it is taking that all the calculate all the distances and take an average of it. So what kind of distance or dissimilarity that you are going to consider, it solely determines, it is going to determine that what kind of clusters that you are going to form here. Is it clear? So this is what is called as a cluster analysis. So the same data, in the same data that what we have shown you for what the recent one we have done, that first of all, so when we talk about this cluster analysis, right, that we basically scale this data first, then we calculate the distance over here, then we have performed a clustering using this H cluster, and we have utilized a complete linkage. So now you have an idea of when we say it is a complete linkage. Then another plot we have drawn which by using average linkage. Another linkage we have done using the single linkage. Right? Now you have the definition of all the linkages, right? Let us try to see what kind of picture we are getting for three different things. Right? So there is a heavy linkage, heavy dependence on actually the what is the linkage type that you are going to get. So when the clusters are being formed, please remember that this whatever the clusters that we are creating with the different kind of linkages, when the clusters are formed, they must be verified with the domain expert, so that whether these clusters are making sense or not. Okay, so I request you to further delve deep into this. But how these clusters are working over here? So this is actually called as a cluster dendrogram, what is being presented over here. So you can actually, this is a tree structure, you can cut it actually. So what does that mean? So cut tree with 4. 4 means what? That I want 4 clusters. So if you cut it over here, you are going to get 4 clusters. So how many lines coming from here? 1, 2, 3, 4. So that means these guys are going to be part of one cluster. These guys are part of one cluster. These whole are going to be part of one cluster. These whole are going to be part of one cluster. And this vertical plots tells, this box plot tells you that it's basically bar plot, not box plot. This bar plot tells you cluster 1 how many observations are there, cluster 2 how many observations are there. Similarly,
Sir,
yes, please.
so please repeat how we decide number of clusters in
Yes,
dendrogram.
yes, definitely. So this different clusters is depending on that. So you, this cluster is clear to you, right? This picture is clear to you. So if we see that, if we tell that I want all people to all individual data to be clustered separately. So that means we are going to have lot of small one. Yes or no? But which is not at all a good idea. So we want an intermediate level. So if we drop it, take it over here, suppose over here, then I'll ending up with one cluster, two cluster, 3, 4, 5, and 6 cluster. Well, anyway, 6 cluster. So in that case, you, what are the number of observations you are going to have in each cluster that you need to investigate. But at the same time, when you are creating different cluster, we must check it out with the individual observation and discussing with the expert over here. Here, after discussing with the expert on that domain, they said that this 4 cluster is enough. Now here please note that I'll just show you additional few figures which will give you an idea that what could be a possible optimal cluster. Let us check it. So partitioning the cluster refers to the classifying observation within the dataset into multiple groups based on their similarity. Right? So the cluster is represented by the cluster center and means. Right? So let us check out. This is not the picture I want to show it for you. So this is what is the optimal number of clusters. So this is one of the plot. This is one of the plot which will be provided, which R will provide it to you, that it will plot the total within sum of squares as a function of number of clusters. Is that okay? Fine. Then this plot will comes, this vertical line, it will automatically show you that after, once we take more than that, there is no significant decrement in the total within sum of square we are finding. Is that answer the question?
Yes, sir. Okay, thank you, sir.
And this plot is very important. Whenever such a clustering result we represent report, then it must be reported that it's a common practice in ecological data science that if we have to represent which package we have used and which function we have used and how using that this being generated. So this must be a part of that, because all the, for example, for PCA there are 5 or 6 methods, other packages are provided. Some packages provide additional rotation, some packages do that. So you are not guaranteed that you will get the exact numerical value for all the packages. So please ensure that every time we need to mention it. There is not going to be very drastic difference, but depending on the algorithms, there is will be a slight difference expected. For example, if you see this cluster over here for this particular data, this R is telling us that 3 cluster is enough. So when you draw these clusters, as you see that this is the cluster plot, you can have this type of plot also, this type of plot also. So depending on the option you will be giving, you can give ellipse type, you can give what type you are going to give, it is going to put a cluster. So it seems that this is good. So if you increase it more, that is a same cluster, different representation. If you increase it more, you will see that you are going to observe a lot of overlapping. Observe that. If you increase more, you are going to get, yes or no? As you see that there are a lot of overlapping stuff is happening. Is it clear? So by doing this experiment with this data, you are able to decide it actually what would be the, and simultaneously discussing with your your other collaborator, your interdisciplinary collaborator, you can decide that seems to be the optimal number of clusters we are getting. Is it making sense? Is it clear?
Yes, sir.
Yes. Oh, okay. Thank you. Thank you. So this is this slide also will be there with you. So here we have performed a facto extra. This is the library what we have utilized to perform this, because automatically when you, as I told you, that when you use more functions or more complicated or more customized packages, we automatically get more and more interesting visualizations. Okay. So this is uh, what is basically the cluster. The codes are will be there with you, and this is a simulated experiment that how the cluster is actually how the k-means function work. Okay, so k-means cluster k is equal, when you run for k-means k is equal to 3, then you see that here I have simulated with 2 clusters only, but additional 1 cluster it is showing. And that packages can help you out that whether 2 we need or we need 3, right? So to run the k-means, for that you do not need any extra packages. So there is a multiple cluster assignments. We have to start with an in start argument. So you can, it's a slight variation is may happen, that what is the initial start you are getting. Okay, so but this is, there is not going to be very drastic changes. Okay, now I think I wanted to discuss about the hierarchical clustering. So what is it actually says? I think I could print a lot of data over here. Yes. So this is the same thing. I think I have already explained it to you, that one is that k-means clustering, another one is that hierarchical clustering. So it is the h-cluster function. So the slides that I have shown, they are what the customized packages we have used for the research publications for our with the work with our collaborators, and this is the without using any packages how we can actually do this. So this is given over here. Okay, so here also you have a complete linkage, average linkage, and single linkage. So you see that how these plots are coming up, right? So again, what are the difference that you need to take out? But definitely one thing is for sure, because here we have simulated the data on our own. So it is clear that single linkage is not working that nicely. Whereas complete linkage and average linkage, they seems to work nicely, because our we have only 2 clusters as per the data simulation that we had, right? So if you check over here, so this is actually the data simulated data. So we know that what are the clusters. We have assigned the clusters on our own. So we know that there are 2 clusters only. So in identifying these 2 clusters, how it performed, as we observe that perfectly identified, right? Our cluster, first 25 observation as 1, this next 25 is as 2. So it's a perfect clustering they have done. Right? So in the same analysis, once we do that, so single linkage does not seem to be a good approach for here, but complete linkage and average linkage, if we put a cut over here, it is able to identify 2. If we put a cut over it, may identify 4. So which may leads to be further small granularization of that. But now we have a package for that, which is going to tell us that what will be an optimal cluster. So for average and complete, they are going to tell you that it is going to be an this what is the optimal one. Okay, so sometimes we can perform the scaling of the features also in the so many applications when our data set is a little bit of and in the when it's particularly when it's dealing with very much multidimensional setting. In that case, it is important that we may have to do it for a kind of a scaling of the data and kind of make the each clusters kind of a data more homogeneous in nature so that our algorithm can identify the data, because one of the points is one of the features which one argument goes little bit up, it may consider it as a different are different as well. So in that case, we need to ensure that that scaling is done properly. This is an exercise for you that you perform a homework on the hierarchical clustering that NCI 60 cancer cell line microarray data, which consists of 6,830 gene expression measurements on 64 cancer cell lines. First, to understand the full complete structure of the data, please don't blindly run that clustering. And then you try to identify and perform a clustering and cluster on this and check out that how many clusters actually they are forming. Okay, so perform a cluster analysis on this data I put. This will contain the main data. So if you just run it over here in CI data, so as you observe that there are 64 rows will be there and 696830 gene expression data will be there. So if you just view this data, so view this data in CI dot. So okay, sorry, it is actually 6,030. So it will be that's why it is taking time. Okay, so this is basically the representative data. Some will be omitted over here, only 50 it is showing, but along this all 64 rows are there. So understand this data, play with this data, and try to perform clustering on this data set. So regarding clustering, my only suggestion will be there, because as so the kind of problems that we have dealt with, the examples which I have shown you, it's not any bookish example or people have said it. So when for the first time also we are interacting with them, because when we present we show we some kind of book examples and everything so that everybody understand. But those who are here research scholars and those who are practitioners, I think it is very important that we play with different options and try to check multiple times that whether we are getting the right thing or not. Because see, free software and a whole lot of packages are there. It requires little bit of verification from our side also. So we should not just take anything whatever is available, whatever it is giving. So we should not consider that. And in this aspect, I'll just remind that particular exercise that Shapiro-Wilkes part. Please do that exercise. It will, at least those who are from statistics background, it will give you a kind of fun. So because Shapiro we very often used, research articles also it represented, but that experiment will give you more understanding about that particular test. Okay, Dr. Joshi, I think I'm already running out of time. I just noticed, and I think I'm left with MDS actually. So,
Okay.
so what to do? So should I just take some 5 or 10 minutes and just show them some picture and
Yes,
stop?
maybe. Yes, yes.
Is it fine?
Yeah, yeah.
So, so all of you, please do not hesitate to drop an email to me, and it is absolutely fine. And we ensure that all codes, all our lectures, everything make publicly available. So there is no issue with that. So I'll show you also to you. So let us just show you couple of things which I wanted to uh, share, because I don't think methodologically, because MDS multidimensional scaling is nothing but a lower dimensional representation of the data. So rather than that, I'll explain you how actually we use it. So that would probably make more sense. So this is, for example, this is recently we have done a certain analysis to understand that how actually that the fish species, how actually different species respond to with respect to the changing climate. So please understand that their question was questioned by the our this environmental scientist collaborators when they have collected the data from some particular region before some environmental hazard has happened, like it was some kind of very big storm, kind of there are big storms are coming up. It already happened previously. So what they have collected the data, physiological information about 7 different fish before before that they had collected the data, and after that event has happened again they have collected the data. So now they are trying to understand whether from a physiological point of view all different groups of species are responding to the climate change in the similar fashion or separately, which are possibly more robust. Is the question clear, that how different fish species are responding to a change in the climate? So let me just make an HTML of this markdown file. At this file, I think I cannot share with you because this is now under revision. But definitely, I'll explain that what is the. I'll share the codes for MDS multidimensional scaling. That is not a problem at all. But complete documentation I will not send. So, and by the time it is getting run, I just want to focus you one aspect, that when you are working in a single RStudio window, so many things actually you can working together. So some file is only R file, .r file, means you have the only script file. You have some of the markdown files, right? And you can just easily access them very easily. Okay. And if you have must have explored it, because there are a lot of options now. They have a Quarto document can also, because you know that recently RStudio being changed to POSIT, so everything is gone there. So now you can make a Quarto presentation which is pretty nice looking actually. So today definitely it will not be possible for me to talk, but our notebook and markdown, definitely whatever the analysis, everything you are looking at, all the work whatever we do and collaborations, everything I use markdown. And some shiny web application, I think the Elora database what we have created, that is one of the application of shiny web app, so that also you can understand. And definitely you can now integrate Python script also over here. You can integrate stand file. Those who are very much prone to Bayesian statistics, to Bayesian, you know that now uh, I think a whole lot of people are actually using stan basically, in particularly because of the wonderful flexibility with the Hamiltonian Monte Carlo method for simulation, because the number of rejections are very less there. So you can run your stan file also there. Then definitely you can write down HTML files, create HTML file, and you can write down our documentation also. So our Swave and D3 script I never used, but others I did use for this work or that work purpose. Let it come. I think it is taking a little bit of time. Let me just see whether I have a PDF ready. Yes, I have a PDF ready over here. So I promise that codes I am going to share so that you can experiment. So this is how something it goes up. So this is actually suppose there is one species over there. It has come over here. This view will be a bit better maybe. Okay, so this is what is that? This is a we have got that collected the data for the physiological response of this particular fish for four different locations. Two locations which are more contaminated, two locations which are not that much, which are less contaminated. Okay. Now one thing is that whether in different location, whether they are physiologically they are different or not. So when you are talking about physiology, there are multiple SDO and SO, and there are multiple measurements, at least 10 different types of physiological measurements. After dissecting them, lot measurements have been taken on that fish. So it is a purely multi-dimensional thing, and two different climatic region or two different pond. There are four total different region. Two of them are similar quality. Qualitatively, one and two ponds are similar. Three and four ponds are similar. Now, whether different ponds has any physiologically impact on this fish species or not, it's a two very much multidimensional scenario. Not able to visualize it. So then, what we did, we perform a multidimensional scaling of the data. So called as a meta MDS is the function by which we do it. After it we do it along the x-axis, we basically got a two-dimensional representation of my multi-dimensional or multivariate data. As you observe that location 1 and 2 they are of similar quality, and you observe that the fish species they are forming a similar cluster in this, and here also for 3 and 4 these guys are more contaminated. There we have a similar structure. So that means in two different conditions, the physiologically the but even this is the same species, that physiological behavior there is a significant change in the physiological behavior. And how that significant measure is done, it is done actually. Say for example, if we consider nmds, that means first axis, so this column, so along this we see, so whether there is a significant spread along y-axis and significant spread along x-axis happening or not. This is the way how we check it. And the mainly the Levens test and the Bertrand test, these are the two tests actually which are carried out. Whether a two-dimensional representation is sufficient or not, to check that there is something called as a stress plot, right? So we performed a non-metric MDS, and this R square is very high. This represents that it is a purely algorithmic representation. May have to run it multiple times to ensure that it is
Hello? Hello? Amiya sir is just joining back. He got disconnected, so he'll be joining in 30-40 seconds. Hello, sir. You have to unmute yourself. You're not audible.
Uh, sorry,
Yeah.
sorry, sorry. Yes, sorry. Okay, so you see that how this statistics, what we do, and how our ecological, biological counterpart, our collaborators know that we did not have any information that which species are of which category. When for each site we plot an MDS for all the species together, you see that this, these two these two are forming separate group. These all are forming a single cluster. And Barton's test and Levin's test, which is the homogeneity of means and variance, which ensured that they are in the same. There is no significant difference. Now, when we talk to them, that is this is what is observing. Are there some kind of different behavior? They said that yes, these are two are different group of category of species. So, which is a different category. So see that whatever we are doing, it must always be matched with them. Now, whether all of them are able to respond to the climate change in the same way or not, so that's being discussed over here. When more contaminated stuff is, you see that when a MDS plot done with the after the climate change scenario on the same species, as we observe that's being broken down, right? This particular two species who are showing a significant deviation as compared to other group of three species. There is the 5 and 7, there is a significant difference has been observed. So it's not that all species are going to respond in the same fashion with respect to change in the environment, and which are going to change in the separately, that can be defined. And this is actually the idea. Using multidimensional scaling, we have tried to give an idea of what is called as an eco-physiological niche. So by niche I concept, we know that niche concepts, we know that what is that? It's basically that the climatic conditions in which a particular species is observed, and the species physiology also very much interacting with that. So we have tried to identify that whether physiologically also two particular species maintaining the same niche or not. This is something what we have tried to address here and define the term called as a ecophysiological niche. Let us hope what is the final thing comes up. And I think this much I have to say. Thank you very much. And please, many codes and many things we make available, whatever our research group are doing. So if you just if you have time and you plan to visit our website, then you will be finding a lot of materials, like particularly niche modeling, where we do a lot of research activities with our collaborators. So, and then you can go in the biological growth curve models. So basically non-linear models and their identification, and also detection of parameter variation. So here we have put actually a lot of codes with description with this. So independently, without any help, we have written in such a way that you can do it. And definitely, and teaching also, if you see over there, so you can get some information about some applied statistics, some machine learning. So some of these ideas, most of the things we have tried not to using existing packages, because those are everywhere nowadays. If you open up YouTube, you will find a number of things. Here we have tried our best to simplify the things, and so that even an undergraduate student can understand a lot of idea wise through various visualization graphically. You are always welcome to drop me an email with any kind of queries. You can always write an email to me, or you can call me also. No problem at all. Look forward to further interaction.